All right, let's do section 9.2, page 454, number 15, which reads, identify the indeterminate form and evaluate the limit using L'Hopital's rule. Support your answer graphically. In this case, we have the limit as x goes to infinity of the natural log of x plus 1 all over the log base 2 of x. So we've been talking about a number of ways that we can evaluate limits, and the first thing to do is always to graph. Well, the graphing is a little tricky here, so we're going to talk about that at the end. And the second thing that we do is substitute in. So let's just substitute in here. So that means that every place that I see an x, I'm going to put in infinity. So I'm going to have the natural log of infinity plus 1 divided by the log base 2 of infinity. And that's going to give me infinity over infinity. So that's the indeterminate form that I have. Now this is actually good because this is one of the two indeterminate forms that lends itself to L'Hopital's rule. So let's remind ourselves what L'Hopital's rule is. It says that the limit as x goes to a, and a can be any number, 0, infinity, 4, of f of x divided by g of x is going to be equal to, assuming that this is equal to either 0 over 0 or infinity over infinity, and a whole bunch of other conditions are met that we talked about when we talked about L'Hopital's rule, then this is going to be equal to the limit as x goes to a of the derivative of f of x divided by the derivative of g of x. And that's going to be a very useful tool. So I've met my condition over here. I have infinity over infinity is my indeterminate form. And that means that I can take the derivative of the numerator separately from the derivative of the denominator and apply the limit again. Well, I'd like to clean this up a little bit before I do that, especially this log base 2 of x. So if you go back almost all the way to the beginning of the book, you'll see that log base a of x is equal to the natural log of x divided by the natural log of a. So here, where we have log base 2 of x, this is going to give us the natural log of x over the natural log of 2. And I'm going to substitute that in because it's going to make it easier for me to take my derivatives. So I'm going to have the limit as x goes to infinity of the natural log of x plus 1 divided by the natural log of x divided by the natural log of 2. Now we've already established that this limit is equal to this indeterminate form and that therefore I can apply L'Hopital's rule. So I'm just going to take the derivative of the numerator and then I will divide it by the derivative of the denominator. So what's the derivative of the natural log of x plus 1? Well, it's going to be, and I'm going to have my limit here, as x goes to infinity, it's going to be 1 over x plus 1. And when I look at the denominator, I'm just going to keep my 1 over the natural log of 2 hanging out here. And what's the derivative of the natural log of x going to be? 1 over x. So note here that I took the derivative separately of the numerator and the denominator. Now I'm going to clean this up a little bit just to make things easier on myself. So I have the limit as x goes to infinity. This is going to become a denominator. And this whole thing is going to become a numerator. Well, if I substitute in, which is really the next thing that I do, I've applied L'Hopital's rule once. Now I should substitute in and see if that application of L'Hopital's rule has solved my problem. So if I just substitute in for x, I'm going to get infinity over infinity again. So applying L'Hopital's rule once wasn't enough. I need to do it again. So I'm still going to have the limit as x goes to infinity, and I'm going to take the derivative of the numerator, and the derivative of x is 1, so I'm just going to get the natural log of 2. And when I take the derivative of the denominator, I'm going to get 1. And now I substitute back in, but I don't have any x's. So my answer is just going to be the natural log of 2. Now, we're supposed to support this graphically. And the reason why it's a little tricky is it's very difficult to graph this. And so what you really want to do is graph that. And when I graphed that, I got something that looked like that, which certainly indicates to me that this function has a limit. And if I looked carefully enough at the check marks on my y-axis, I would probably be able to figure out that it is the natural log of 2.